Hello and welcome to this manufacturing process technology part 2 module 24. We were talking about the estimation of the tool shape given a particular workpiece shape, and if you have a functional representation on the workpiece side, can we really map what is going to be the inverted tool surface. So, in respect of that, let us say the coordinates of both x as well as y are selected so that the y axis and the feed direction are parallel. So, let us consider only a two dimensional case where there is no variation in the z direction. So, let us suppose this is the xy coordinate system which we are talking about, this being the y direction, this being the x direction, and further we have been given a particular work surface profile which follows a functional relationship. So, the work surface geometry here is prescribed to be y equal to phi x, and let us suppose there is a point here P which is determined by the coordinates x w and y w, and further the work surface follows a functional relationship y equal to phi x. So, the goal really here is to determine what is going to be the tool surface. So, this let us say is the predicted tool surface, and let us say corresponding to this point P w, there is a point which exists exactly opposite to the point P w of the workpiece. We call this point P t. So, this has coordinates x t and y t. So, given this relationship on the workpiece side, we have to see what is the kind of functional relationship which happens on the tool side. So, further this is a case where the work is actually moving at an inclination angle theta with respect to the tool surface. So, let us say if the tool surface goes like this is how the workpiece is going to move, and if I were to just connect the surface P t with respect to the perpendicular, there is a point here which it makes, we call this the point A, okay, whereas this origin is O. Further, the gap between the 2 points opposite to each other in a perpendicular direction, this gap is given by the equilibrium gap G e. So, having said that, now let us try to map the function that exists on this side, tool side, which we have to obtain from the parameters given like x w, y w and the functional relationship on the x side. So, here at a steady state condition, the gap between a point on the workpiece surface P w given by x w, y w and the corresponding point on the tool surface is given by Pt x t y t would be given by P w P t equal to the equilibrium gap G E. So, obviously, from the illustration that has been drawn earlier here, what we can find out is that the x t, which is actually all the way here from the origin, minus x w, which is here, would be given by this distance right here, which is nothing but the equilibrium gap G times of sine of theta. So, let this be one of the equations, let us say equation 2, and the other one is in the y direction. So, let us assume the y coordinate here as y w and the second y coordinate all the way here as y t. So, y w minus y t should be equal to G cos theta. Let us assume this to be equation 1. We already know that. So, let me just write this down here. So, we have equation 1 as y w minus y t, okay, G cos theta, and equation 2 as x t minus x w equals G sin theta, equation 2. So, we already know the value of the equilibrium gap, particularly from the process parameters. It is given by conductivity times of the atomic weight divided by, or times of V minus delta V divided by the rho z, the Faraday constant capital F times of feed cos theta. So, that is how you estimate the equilibrium gap, as I have shown earlier several times in other occasions while calculating the MRR. So, having said all this, there is a possibility of mapping y t into x t, given that there is a functional relationship which already exists between the y w and x w. So, let us try to explore that point here. So, we can easily say, therefore, y t becomes equal to y w minus of obviously k a v minus delta v divided by rho z f f cos theta times of cos of theta, cancels out. We are left with y w minus some lambda by f, where lambda is this whole expression k a v minus delta v divided by rho z f capital. So, this is how we had also earlier defined the equilibrium gap, particularly when investigating the dynamics of the tool with respect to the workpiece. The second equation obviously results in x t equals x w plus k a v minus delta v divided by rho z f small f times of sine by cos theta or tan theta, okay, and this can again further be written down as x w plus lambda by f tan of theta. So, this is the modified 1 and 2 equations as has been shown earlier. So, tan of theta further can be estimated as the slope d y w by dx w at the point p w x w y w. Let us go back to the figure and have a look at how it is the slope. So, tan of theta is basically really the tangent at this particular point. So, it is about how dxw or yw varies with respect to xw at this point xw yw. So, having said that, now the tan theta can be substituted in the above equation, and I can write x t to be equal to x w plus lambda by f d y w by d x w. Also, since the workpiece geometry is given by y equal to phi of x, therefore, dyw by dxw can also be written as d of phi xw by dxw. So, I am going to further put this back here to find out what it results in, and probably I can show you a little more detail just to understand this slope concept, which may be from the geometrical idea it can come out. So, this is the workpiece surface and the tool surface. These are the two opposite points P w and P t, which are connected and they are perpendicular to each other, and I am talking about the feed direction theta in which this particular workpiece moves towards the tool surface. So, if I looked at the tangent at the point P, which is represented by again tan of theta okay, dyw by dxw at the point Pw. So, I can actually try to draw another right angle here, let us say A dash P w O dash, okay, in which this angle is already theta. Okay. So, this obviously in the right triangle given by this area here becomes pi by 2 minus theta, and so in this right triangle A dash P w O dash, this becomes again theta. So, really it is tan of the same theta, that is the inclination direction with respect to the equilibrium gap. Okay. So, that is how we assume tan theta. So, therefore, the y t can be simplified or just written as y w minus lambda by f, and the x t can be written as x w plus lambda by f times of dy w by dx w. In other words, from the y w what we can interpret is that y w, which is otherwise a function of x w phi x w, can be written down as y t plus lambda by f, and as we already know that now x t has been included in x w somehow. So, x w can be further written as x t minus lambda by f times of d phi x w by dx w. We are just simply representing the y w value here in this expression. So, obviously then the y w, okay, which is a very well a function of the x w, can be written as y t plus lambda by f equals phi of the new value for the x w, which is lambda by f d phi x w by d w. dx w. That is how you write the final form of the expression, which is a map of the yt into the xt, given the map on the workpiece side of y into the x on the w or workpiece side. So, if x phi x w is specified as a function, it may be possible to express d phi x w by dx w, what we did in the last step, as a function of x t completely, which is our goal really. So, we want to find everything in terms of y t and x t and y t. So, therefore, the tool geometry is represented by y equal to phi x minus lambda by f times of this function here phi x t y x y t, which is actually the how you represent the slope of the function d phi x w by dx w as some function phi of x and y minus lambda by f. That is how you represent the tool side relationship. So, let us actually look at an example to get a little more feel about what we want to say here. Let us suppose we have a relationship on the workpiece side y w given by a plus b x w plus c x w square. So, this is the y equal to phi x w. So, now we want to map the tool surface from the logic that has been represented above in the few slides. So, in this particular case what I would like to express is that already we know the relationship y t equals phi of x t minus lambda by f xi of x t y t minus lambda by f. Okay. So, this is all of the tool surface relationship that we are obtaining for the coordinates which are there on the tool surface. So, we do the same thing. So, we already know that y t equals y w minus lambda by f and x t equals x w plus lambda by f times of del y w by del x w. So, obviously, as y w is given as a plus b x w plus c x w square, the d y w by d x w now is given by b plus twice c x w. Okay. And what I can probably say here that if I wanted to put back in terms of x t what is x w. So, basically you can write it as x w lambda by f b plus twice c lambda by f times of x w. Again taking this off, we have x t equals x w times of 1 plus twice c lambda by f plus lambda b by f. In other words, x w can be x t minus lambda by f, lambda b by f divided by 1 plus twice c lambda by f. So, if I were to put this back into the formulation, so you already know that y w is related to x w in the way a plus b. Now, the value of x w is now done here, which is x t minus lambda b by f divided by 1 plus c lambda by f, okay, plus c times of the square of x. So, x t again minus lambda b by f divided by 1 plus c lambda by f whole square, okay, value of x w, and this y t y w is again written as y t plus lambda by f. So, that is how you express this thing. So, if I simplify this term together, I would actually have y t equals a plus b x t, okay. And if I wanted to just play around this term, and then I do not want to simplify this in great details, I mean algebraic details, but it is just about if you probably just add these terms together, one obviously has 1 plus 2 lambda c lambda f square. So, in this particular case then I can get a plus b x t plus c x t minus lambda by f times of the term that I am expressing here as b plus twice c x t square divided by 1 plus twice c lambda by f. So, this is actually more like an approximate solution of this value of y t equal to this whole expression which is here. So, I can actually now predict the relationship between the y's and the x's on the tool surface given the values or given the functional relationship on the workpiece surface. Let us look at the overall problem for just for the sake of theoretical clarity. There is a geometry of the workpiece surface with a single curvature which is given by this equation now, y is equal to 10 plus 0.3 x minus 0.05 x square, x and y are both in centimeters, and the process data are that the applied potential is about 15 volts, over voltage in this case is 0.67 volts, the feed velocity is 0.75 millimeter per minute given to the work in the minus y direction, work material is equal to copper, and the electrolyte conductivity is also given as 0.2 centimeter inverse ohm inverse, and we have to determine the equation of the required tool surface geometry when the workpiece geometry has been given by this y equal to this functional relationship between y and x here given here in this part of the question. So, we find that for copper the values that we have to assume is that it dissolves, let us say, at a plus 1 valency. So, the minimum dissolution limit is like plus 1 for this copper, and the atomic weight is about 63.57 grams, and the rho that is the material density is about 8.96 grams per centimeter cube. We have to find out what is the value of f. So, what is, so basically we already know that the value of f is 96,500 coulomb, and the feed velocity in this particular case comes out to be equal to, the feed velocity in this case comes out to be equal to f 0.00125 centimeter per second. We find out that as lambda equal to K A divided by V minus delta V by rho times of Z times of F, and we can actually calculate this lambda value as 0.2 times of 63.57, the value of the atomic weight, times of 15 minus the over voltage potential which is in this case 0.67, okay, divided by the total material density 8.96 times of the dissolution valency which is univalent in this particular case, assuming it to be univalent, times of the Faraday constant. So, this many centimeter square per second of lambda is recorded. So, this is 2.11 10 to the power of minus 4 centimeter square per second, and so lambda by f typically in this case becomes 2.11 10 to the power of minus 4 divided by centimeter square per second divided by 12.5 10 to the power of minus 4 centimeter per second, which is actually calculated or converted from this 0.75 millimeters per minute feed velocity, and this in centimeter is reported to be 0.169 centimeters. So, having said that, now the phi x or the functional relationship between the workpiece x and y coordinates are explored as given in this equation, phi x equal to 10 plus 0.3 x minus 0.05 x square, and the final equation for the tool surface geometry from the derivation that has been done in the earlier step. So, final equation for the tool surface geometry is found by equation y equal to 10 plus 0.3 times of x minus 0.169 that is the lambda by f times of 0.3 minus 0.1 x divided by again 1 minus 0.1 times of 0.169, and this is the converted value of the x coordinate on the tool side given the functional relationship on the workpiece side minus of 0.05 times of again x minus 0.169 times of 0.3 minus 0.1 x square divided by 1 minus 0.1 times of 0.169. Okay, so this actually whole square here and minus of 0.169 the lambda by f term. So, we simplify this equation after solution and we arrive at a formulation 9.8154 plus 0.3157 x minus 0.0517 x square as the final tool surface equation. So, given the workpiece relationship in the question, I can now find out what is the relationship between the position coordinates y and x on the tool surface, where both x and y are in centimeters. So, this is typically how you estimate some of the theoretically the tool surface or the tool shape given a certain functional relationship which exists on the workpiece shape. So, it is all about mapping, because ECM is really a die sinking process. It has to really comply to that the tool surface is exactly the negative of the workpiece surface, and for this such a formulation is actually kind of valid. So, if supposing the tool geometry were to change, and supposing now if I were to say that the tool geometry is a 3-dimensional surface where y is represented as a plus bx plus cx square plus dz plus ez square. Now, it depends on both x as well as z. So, in that event the final formulation of the transformation into the tool side would actually have y equal to a plus bx plus cx square plus dz plus ez square plus gxz minus lambda by f times of a whole term here b plus twice cx plus gz square plus cd plus twice ez plus gx, this again so I am sorry bracket d plus twice ez plus gx whole square divided by 1 plus z times of c plus e times of lambda by f. So, this is again using the same transformation as I had earlier done. It may be food for thought, or maybe you can try to solve by looking at this function relationship and then substituting the way that the tool coordinates express into the workpiece coordinates and try to make a map of the function of the workpiece on the tool surface to arrive at this particular formulation. So, in any event I will probably give a complete solution to this particular how it is formulated in a later on module, okay, of our work. So far you have in ECM covered various topics like how to design for the velocity of the electrofluid flow, what are the different criteria which will result in different surface roughnesses, what is the basis of the tolerance in the ECM process, and then finally you are able to estimate the overall shape and size of the particular tool surface given a certain shape requirement that we have on the workpiece surface. So, I would like to now sort of end this module in the interest of time, but in the next module we will start with another version of our issues related to the the non-uniformity in the MRR or the material removal rate, which is based on the improper flow of the electrolyte and the way that the flow separates over a surface, particularly surfaces which may have disruption in terms of sporadic dissociation and other mechanisms as have been described before. So that we can see that how eddies and vortices and flow separations along the path of the flow may result in a completely sort of a gradient MRR or a difference in the MRR at different zones of the machining. So with this I would like to end this particular lecture. Thank you for being with me. Thank you.